So welcome everybody to the Govind Swarup Memorial Lecture of 2026. Um, all of us, this award lecture was started about 5 years ago in 2021 in honor of Govind Swarup, the father of radio astronomy in India, after his demise in September 2020. And we've had five lectures until now. So most of us in the audience knew Govind fairly well, but I'll only say a few words about Govind, mostly for the younger people in the room. So after Govind returned to India in 1963 from the US, he basically started radio astronomy in India, and he put together an outstanding group of people and started radio astronomy by essentially building radio telescopes, starting with the Kalyan dishes just outside Bombay, moving on to the Uti radio telescope in Uttakamand, and then culminating with the giant beta wave radio telescope, which many of us have used over the last 25 years or so. And along the way, he and along with Rad at RRI, I think both people deserve credit for this, they essentially built the radio astronomy community in India. And that meant that today we have a whole bunch of radio astronomers which didn't exist in the early 60s. And that, I would say, is a huge contribution. So Govind is, of course, an outstanding scientist. He did all kinds of things. He started off with low-frequency studies of the sun. He did lunar occultation studies. He did 21-centimeter observations of high-redshift galaxies. He did cosmology. He dabbled in all kinds of stuff. Essentially anything that was, cutting edge and could be done with his baby, which is low-frequency radio astronomy, he would like to do. And he always wanted to know what was the exciting thing to do at any given point of time. And the GMRT came really from that. But in addition to being an outstanding scientist, he was also hugely imaginative, especially in telescope building, telescope design and building. And the hugely innovative designs of the ORT and the GMRT are testimony to that. He was also an extremely approachable person, one of the most approachable people that certainly I've come across, and very excitable. Many of us who were around in the 90s will remember that the corridors of NCRA were full of people who had essentially met Govind, scattered off Govind for 5 minutes, for a 5-minute chat in the corridor, and were still there 3 or 4 hours later, chatting away happily with Govind and somewhat exhausted, while Govind was still full of energy. And he loved chatting with people. And this ranged from, it didn't matter who you were, whether a faculty member or the junior most student, he would chat with you quite happily. And he was, so he loved telescope building. He loved doing science with telescopes that he had built. He especially loved the GMRT. But in addition to that, he also had a great sense of humor and fun. And he didn't take himself too seriously. He could actually see the lighter side of himself. And one of the things, he's one of the few genuinely inspirational people whom I have ever met. He was a person that when you chatted with him about something that he was excited about, and he was full of excitement about things. When you talk to him, you would kind of not notice any of the difficulties that there would be in what he wanted to do. You would just see the excitement of the thing that he wanted to do, and that was worth doing. And you would feel like doing it. It didn't matter how challenging it was. And that is probably why he was able to attract and inspire so many young astronomers and engineers, right in the 60s, all the way down till the building of the GMRT. He could really excite them, and he could kind of make them not worry about the difficulties and take on these very challenging projects. I can't tell you how hard it would have been in the 80s to dream of building the GMRT in India at the time, let alone actually doing it. Even to think about it would have been hugely challenging. So he had courage, huge courage. And this ability to think about what is important and to carpe diem, to seize the day, to go after challenging things without worrying about difficulties, with the confidence that if difficulties come, they can be solved, they will be solved. That was something which I think he has bequeathed to us. And that probably is his greatest legacy to the Indian radio astronomy community. And so, many of us love Govind, and it is really sad that he's not with us today. But so today we'll have Bernie Fanaroff giving the 2026 Govind Swarup Memorial Lecture. And the title of the lecture is Govind Swarup's Legacy and South Africa's New Telescopes, whose Govind, of course, influenced people around the world with his style of doing science. Bernie is it's a huge pleasure to introduce Bernie to all of you. And I'm just really sad that Bernie wasn't able to make it here today, despite valiant attempts to come here. Just the situation in the world is complicated. But Bernie is perhaps the foremost example in astronomy of a really rare combination of an outstanding scientist, which is not all that uncommon, but more importantly, an outstanding human being, and who has had impact far beyond the field of astronomy, far beyond the field of science. And that is something which is really uncommon in science. We have a lot of people who do great science, but Bernie is just an outstanding human being. He's an outstanding person. So he got his bachelor's degree, his BSc honors degree in physics in 1970 from the University of the Witwatersrand in South Africa. And then he moved to England, where he did a PhD in radio astronomy, which he finished in 1974 at Cambridge. And during his PhD, he and Julia Riley came up with what has come to be known as the Fanaroff-Riley scheme of classifying radio galaxies based on their luminosity and size in the sky. And that is still something that forms the basis of our understanding of radio galaxies and active galactic nuclei today. So he has had an impact very directly on science, more than 50 years later. But Bernie moved back to South Africa after his PhD, and he joined the University of the Witwatersrand as a lecturer in astronomy. He then resigned to the university in 1976, and he became an organizer for the Metal and Allied Workers Union, and then later for the National Union of Metal Workers of South Africa, where he was the national secretary from 1987 to 1994. And in 1994, when Nelson Mandela became the president of South Africa, Bernie became the Deputy Director General in President Mandela's office. And for the next decade or so, he basically served the government in a variety of roles, including, perhaps most importantly, he was the head of the Office of Reconstruction and Development Program in South Africa. I can't tell you how important a role that was. And Bernie came back to astronomy in 2003 as the head of South Africa's SKA project, SKA BID. And he continued in that role until 2015, until he retired in 2015. And he continues to act as an advisor to the South African Radio Astronomy Observatory, to the South African SKA folk, even today. And he basically steered the South African community towards a successful bid for the square kilometer array. As you probably all know, the square kilometer array bid is going to be built in South Africa. And Bernie played a crucial role in getting this telescope to South Africa. But even more important, probably crucial for South Africa, Bernie realized fairly early on that in order to build the SK and to do great science with it, he would need to establish a community of young astronomers and engineers in South Africa. And so what they did was that they managed to get the government to set up funding grants to attract young people to astronomy. And that was hugely successful. If you go to South Africa now for conferences, you will see a whole bunch of young South Africans full of excitement about doing astronomy. And that is something that Bernie has contributed directly to, again, remarkably like Govind. In addition to that, Bernie also pushed very hard to build a precursor for the square kilometer array. And that turned out to be the MeerKAT telescope, which is one of the finest radio telescopes in the world today. And Bernie, again, directly played a role in that. So as I said, Bernie is an outstanding scientist. He's gotten a large number of accolades of all kinds. He's an FRS, a fellow of the Royal Society. He got the order, the Mapum Gubwe of South Africa for excellence in public service. He was also the Jansky lecturer of the National Radio Astronomy Observatory. And so for his outstanding science, and perhaps even more for his outstanding contributions to building telescopes and building an entire radio astronomy community in South Africa, he was a man very much after Govind's own heart. And I know that Govind has talked to us about him. I know that Govind held Bernie in the highest possible regard. So it is a huge pleasure for me today to invite Bernie to give the Govind Swarup Memorial Lecture for 2026. Welcome, Bernie. I'm sorry you can't be here, but you have the floor.
Thank you very much. Thank you very much for that introduction. And I do apologize that I can't be with you today. We were looking forward to being in India, to meeting all our friends. I'm very sorry it couldn't happen. I hope it will happen again in the future. But it is a great honor indeed to be able to speak about Govind. Govind was a good friend to us in South Africa. as you say, a wonderful man, a wonderful astronomer, a very approachable person. And it's a great honor to be able to say that much of Govind's vision was shared by us. And part of the vision, which I think is crucially important, is that Govind clearly believed that you can do cutting edge research in what is now called the global south. And we believed that too. And our vision was to make it happen. So, sorry, let me. Okay, so as you've explained so well, Govind's vision was to bring India into the forefront of world radio astronomy. He knew that he had to build both the science and the people and the technology and raise the profile of sophisticated blue sky science in what were then known as developing nations. So Govind was a pioneer and an innovator. And you've already said that because of the limited resources in India, he had to be exceptionally innovative in designing and building the Uchi telescope and the GMRT. Govind understood, and we also understood, that large science instruments are very visible and they're exciting for politicians, for young people, and for the public. Another thing that Govind understood, and we also understood, is that to be successful in any major enterprise, and establishing radio astronomy in India or South Africa was a major enterprise, you have to have critical mass. You can't spread yourself too widely. You've got to focus your effort and you've got to focus your investment. And one of the best ways to do that is to build very large and very visible telescopes. But you can't build a telescope efficiently in the traditional university laboratory. Govind understood that, and he drove the establishment of the National Center for Radio Astrophysics, a dedicated professional institution. And as you said, he built up world-class research with these limited resources. Our project, our square kilometer array project, has so many parallels with that. We decided to build innovative telescopes with our limited resources so that we could focus both our effort and our funding. We wanted to raise the profile of blue sky, cutting edge science and technology. We wanted to bring young people into science and technology careers. You've already mentioned we had to build a cohort of outstanding researchers, which I think we've been able to do. And in order to do that, we did very much what Govind did. We created a dedicated institution called the Square Kilometre Array South Africa Project, which is now the South African Radio Astronomy Observatory. As you know, in 1994, South Africa held its first democratic election. President Mandela was elected president, and in 1996, the government published a white paper setting out a science policy, and it made a number of very important points. First of all, it said, we don't want to remain a second-class nation who are only allowed to do research on food and water and housing and so on. We believe that we have as much competence and as much right to do cutting-edge research in physics and astronomy as anybody else. The white paper also said that we have certain geographical advantages, and two sciences in particular were identified. One was astronomy and the other one was paleontology. As you know, Africa and Southern Africa in particular are the home of Homo sapiens and, in fact, most early humans. So astronomy has a history in South Africa. It didn't come out of nowhere. The San people, who are among the oldest indigenous people of modern humans, had a cosmology, and some of the illustrations of that cosmology are shown at Jodrell Bank at the Square Kilometre Array headquarters. The British established the Royal Observatory at the Cape in 1820, mainly for navigation, but the Herschels and others did very important work there. Later, the South African Astronomical Observatory was established at Sutherland, which is on the edge of South Africa's Central Plateau, and built the 10-meter SALT telescope, the Southern African Large Telescope, in which India is a partner. And that saw first light in 2005, and there are now many international telescopes on that mountain in the small town of Sutherland. The only radio astronomy observatory was at Hartbeespoort near Pretoria. There was a 26-meter dish which was left behind by NASA in 1976 when they left South Africa. It was part of their deep space network. And that was converted for radio astronomy and did a lot of VLBI work. So in 2003, we had a situation where we had one telescope and 5 radio astronomers, all of whom were white men. The president of the National Research Foundation at the time was Dr. Khotso Mogele. And after the groundbreaking for the SALT telescope, he challenged astronomers to think big and to decide what the next big thing was. And it was decided and supported by our National Department of Science and Technology and the National Research Foundation that South Africa, with African partners, should bid for the site of the Square Kilometre Array, which was to be the biggest telescope ever built, an interferometer, which was to be spread across 2,000 kilometers. So in 2003, South Africa, with 8 other African countries, submitted an expression of interest to host the Square Kilometre Radio Telescope. And we got full support for that from the South African government and the African Union heads of state. In 2006, Africa and the Australia and New Zealand bids were shortlisted. In 2012, an international independent committee recommended the African bid, but the SKA International Board decided to split the telescope in 2012. And as you know, the mid-frequency telescope, the dishes, are now under construction in South Africa, and the low-frequency telescope is being built in Western Australia. We had some advantages when we started our project to build radio astronomy in South Africa and to make South Africa a leading nation in radio astronomy in the world. One was that Rob Adam, who was the head of the Department of Science and Technology, and I were both friendly with a lot of the cabinet ministers. As you've said in your introduction, I was Deputy Director General of the Presidency, and you can see in the picture the President's office in Pretoria and the President's office in Cape Town. South Africa is an administrative capital in Pretoria and a parliamentary capital in Cape Town. So that gave us access to a lot of decision makers. And like Govind, we asked the question, can we look beyond the horizon? What needs to be done, but currently seems to be impossible? We had a vision like Govind. We were able to quickly build a team which was committed to the vision. Like Govind, I was a very strong believer in carpe diem and apologize later. If there's an opportunity, seize the opportunity. If it works, people will be very happy. If it doesn't work, they'll fire you, but that's another problem. There was one problem that we did face, and that is that there was a lot of Afro-pessimism. That is, a lot of people, both in South Africa and in other countries, said quite loudly that it is impossible to build sophisticated science infrastructure in Africa, and they just didn't believe we could do it. But of course, as you know, it did go ahead, And this is just a picture of the countries which are currently involved in the International Square Kilometre Array project. There are a very large number of them. And as you can see, this is a map from last year. Those countries cover the world. India is a leading partner, South Africa, China, Canada, the UK, France, Germany, Switzerland, Australia. So it covers the world. It's a really international project. We have 8 African partner countries. They're not directly part of the treaty organization, but they're represented by South Africa in this. So what we've done in South Africa to prepare for the building of the SKA mid-frequency telescope is to buy up a site from the farmland in the very arid area in the center of South Africa called the Karoo. South Africa is divided into provinces. This is in the Northern Cape province. So the National Research Foundation has bought 130,000 hectares for the core of the telescope and has secured 92 servitudes for the outlying stations. And a law was passed in 2007 by Parliament that gives the power to the Minister for Science and Technology to make regulations covering the whole of the Northern Cape province, which will prevent any activities which could interfere with radio astronomy or optical astronomy. And the whole 130,000 hectares has now been declared to be a wilderness area, and it's managed by the government organization called South African National Parks. So this is a picture of South Africa, bottom left. You can see blue is where people are, and you'll see around the area of the telescope, there are very few people. The bottom left is Cape Town, the top right is Johannesburg, but around the telescope, there are very few people. And that whole area is covered by regulations now in terms of this law, the Astronomy Geographic Advantage Act. We were lucky in that our steering committee for the project was composed of the Director General of Science and Technology and the President of the National Research Foundation, plus a few other people. And we met initially every week, then every month. So we were able to make decisions very quickly. And in 2004, the steering committee decided that we should get involved in SKA technology development. We didn't just want to offer a piece of land. Initially, we thought we would have to be junior partners. We would work with some other countries and help them developing technology. But we quickly realized that our own engineers were world-class and we didn't need to assist anybody. We could do it ourselves. So in 2005, we decided to build our own telescope as a precursor to test out the concepts of the square kilometre array. And again, there we were lucky. Our steering committee trusted us as the team to do the job, and they focused on the strategic issues and the funding and left us to get on with the design and building of the telescope. So our mandate from government was that we must build the best telescope to do the best science. Our impression was that many of the other countries in the SKA consortium had to tell their governments in order to get funding that they were going to develop cutting-edge technology which could be commercialized. We didn't have that pressure. We just had to get on with building the best telescope. We wanted to make South Africa a center of excellence in the world in astronomy. We had to bring young people into science and engineering. We wanted to build a large and very dynamic group of young astronomers and technologists. We wanted to develop expertise in South African industry that would be internationally world-class. A very important instruction was to transform astronomy to include women, black scientists and engineers, of whom there were very few at the time. We also had to use the construction of the telescope to develop the local economy in the Karoo, which is a very, very poor area. When we arrived there, the small town of Carnarvon, which is where the telescope is headquartered, had an unemployment rate of about 80%. We also had to build centers of excellence at the universities, and of course there was the usual instruction, don't go over budget. So, as we've already said, Govind knew that you couldn't build very large telescopes like this in a university laboratory. So we decided to run the whole project as a professional engineering project, both the acquisition and infrastructure of the observatory and the building of what became known as our MeerKAT telescope. It was a project of the government, so it was funded by government, it was run by government, but Rob Adam, as the head of the Science and Technology Department, and Khotso Mokheli, as the president of the National Research Foundation, made sure that we were outside the bureaucracy so we could move quickly and we could be very agile. So we quickly put together a dedicated team of very skilled engineers. We found out very quickly that South Africa had very highly skilled radio and radar engineers, antenna engineers, and so on. They knew nothing about astronomy, but they were very excited about the challenge that we presented to them. And we were able to get the best people because it was the most exciting project around. Now, at the time, there was a belief in the SK international community that the most we would ever get out of the funders was about €1 billion. So we had to fit the SKA into the €1 billion budget. And in order to do that, there were some beliefs in the SKA community at the time that we needed certain quick fixes in order to save costs. So one of them, for instance, was that you could build telescopes with what we call a dirty beam. In other words, an imperfect telescope beam. And you could sort out all the problems in data processing. And of course, as we found now, that's not really possible. It's not really viable. Another very strongly held view was that in order to get high survey speed so that you could cover the whole sky quickly, we should focus on very wide instantaneous field of view. And so a lot of time and energy and money was spent on developing focal plane arrays and aperture arrays, which generate many simultaneous beams and cover the sky very quickly. They've taken a very long time to mature. And in fact, I think are only really becoming mature now. We decided not to go that route. Another belief was that you could outsource everything to industry. What we realized was that you can outsource some things to industry, but you've got to have the skills inside to be able to manage industry properly. Otherwise, they don't do what you want because they're just not used to the kind of very, very tight requirements that radio astronomy has. So we decided to save costs by very, very careful engineering, by optimizing the design and construction at every stage and paying fanatical attention to detail. And our engineers did that superbly well. So we built a general purpose telescope. It's now 64 dishes, 13.5 meters in diameter, spread over 7 kilometers. We decided to build the best possible beam, and we decided on cooled single pixel feeds. So these are cryogenic feeds and receivers. We decided on an offset Gregorian design. I'll show you a picture of that. So there are no obstructions in the beam, which could make it imperfect. We focused most of the dishes in the central part of the core so that we could image very faint and diffuse emission, and that's been one of the strengths of the MeerKAT. We decided to optimize sensitivity and dynamic range for the best imaging. Dynamic range is so that you can see very faint objects, even when you've got very bright objects in the field. And we aim for high survey speed, not through very wide field of view, but through very high sensitivity. And we did, in fact, achieve that. There's wide frequency coverage. There are now UHF, L-band, and S-band receivers on the telescope, and new receivers are being built. There's very good frequency and spatial resolution. You can go up to 32,000 channels and 7 arc-second spatial resolution in the L-band. A very important requirement was very accurate timing for pulsars and other applications which required timing better than 7 nanoseconds. And a very, very innovative idea was to allow commensal observing by broadcasting the data which came from the dishes, not only to our correlator and beamformer, which combines the signals from all the dishes, but also to user-supplied equipment. And I'll talk more about the user-supplied equipment. So many different groups can use the telescope at the same time. There were a number of success factors. One of the very important success factors was that we were very modest. We had some very competent people as astronomers, but there were very few of them, and they didn't claim that they were world leaders. So we had no gurus who could tell us that they knew exactly what had to be built. We just had to get on with it and build it. Instead, we used a system engineering process. We used quite a strict system engineering process with some flexibility because research and development is required. It wasn't easy to persuade all our people, especially software people, that system engineering was a good idea, but we did that. Bit of stick and carrot. We ran it as an engineering project. We didn't let scientists interfere too much because scientists always want to extend the scope. And as I said, we had full autonomy to get on with it. We built lean, highly skilled, dedicated, and excited teams of engineers and very small and agile teams for each of the subsystems of the telescope. I gave full autonomy to each of those teams within the system engineering management plan. My view was that they know what they've got to do, they must get on with it and just not mess it up. There was a system engineer allocated to each team to make sure they remained within those management ideas of the system engineering management plan. And we outsourced quite a lot, but under very strict conditions and very strict supervision. So just very quickly, the system engineering process is you ask the users what they want. What do you want to do with this instrument? And they tell you, they give you a user requirement specification. Then the engineers go away and say, what kind of telescope do we have to build to give us that user requirement? And then you break it down further to the subsystems. What kind of subsystems do we need to build that system with that performance? And then you go down to component level. And all the way, you have to manage the interfaces to make sure they integrate properly. And you also have a verification process, which goes on at all stages, testing what you're doing. And of course, one of the reasons for doing it this way is that if you make mistakes early on in the project, in the concept or design, it's fairly easy to correct and it's fairly cheap to correct. If you make mistakes and you identify them only later, it's very expensive to re-engineer things and it's very difficult. So system engineering, in our view, was very important. So we initially bought land on a farm called Losberg in the Karoo, and we put up infrastructure. You can see in the picture, these are old pictures I took more than 10 years ago. There's a very large shed where the dishes are assembled. There's a buried underground bunker where our uninterruptible power supplies and computers and mazes are housed. You can see in the bottom left, there's 2.5 megawatts of rotary uninterruptible power supply. And on the bottom right is the shielded rack room, which is now full of computers. Of course, in those days it was empty. So along the way, we built 2 prototypes. The first one was a 15-meter fiberglass dish, the largest ever made, which was built at the Hartebeeshoek Observatory in Pretoria and is now used for science. And we tested and did a lot of tests on fiberglass, whether you could use it. We tested focal plane arrays and we decided they were too immature for us to use. Then we had to do another prototype in the Karoo because it's obviously different building something very close to Pretoria than it is building somewhere which is a 9-hour drive away from Cape Town or Johannesburg. So we built a 7-dish Karoo array telescope prototype, 13-meter fiberglass prime focus dishes with cluster feeds. And we tried Stirling coolers because we thought we'd be able to get them cheap because they're used on mobile phone masts, but they didn't work well enough. So we ditched them and we reverted to the traditional cryogenic coolers. So in our final tender, we hoped we'd be able to go with the fiberglass, but it came out too expensive and we ended up with metal dishes. So we have 64 13.5-meter metal dishes. The offset Gregorian, as I said, is to keep design where there are no struts to obstruct the beam. We have single pixel cryogenic receivers. One of the major innovations was that the radio signals are digitized on the dish. Now that's a risk because digitization creates radio interference, so you have to design the digitizers very, very carefully so that nothing leaks out to get into the receivers and the amplifiers to make noise. We also built the buried and shielded building that I showed you. And at the end of the project, we had no budget overspend. We had a 1-year schedule slip because we had changed from prime focus to offset Gregorian. So the engineering process worked well. This is a picture of what the dishes look like. You can see on the right the main reflector, the sub-reflector, and then on the bottom left you can see the turntable with space for 4 different receivers. And in the middle there you'll see our cryogenic receivers. The company EMSS, which worked very closely with us, designed very, very small feeds and receivers which could fit into a cryogenic vessel with maximum efficiency. So some of the innovative things that happened, first of all, system engineering wasn't widely used at the time in astronomy. We optimized performance and cost at every stage, which again was not well thought of at that time. Digitization in the dish was new. Very small OMT and receivers to fit into the small cryostat. There was a lot of innovation of hardware and firmware. We ended up with receivers which were twice as good as we had specified, so we got 4 times better survey speed for the same price. Of course, there is radio frequency interference, both from external sources like satellites and TV stations and mobile phone stations. But there's also internal RFI. Any electronics which has digital processing creates interference. So the teams have designed very innovative ways of excluding radio frequency interference. And one thing that is very important is that every single piece of equipment which goes onto the site, whether it be a car or a radio receiver, is tested for radio frequency interference. So the commensal observing I spoke about and the user-supplied equipment is very important. So the signals go to our FX correlator and beamformer. That's for imaging and for pulsars and a whole range of other things. But there are specialized equipments on the end of the telescope again, one for pulsar timing, one for transient search, one for techno-signatures, which is built by the Breakthrough Listen project. And all of these have been built together with the South African Radio Astronomy Observatory and universities across the world, Swinburne, Manchester, Max Planck Institute, and so on. And all of this equipment is accommodated in the MeerKAT buried rack room There's a support base at a farm called Clairefontaine, 80 kilometers from the telescope. We had to design a specially low noise power line from Carnarvon to bring electrical power to the site. Low noise means it doesn't spark, it doesn't create corona. We had to put in optical fiber to the main national backbone. We had to build 80 kilometers of new roads. There are workshops, there's a chamber for RFI testing, and there's a training center for artisans. One of the big problems which faces the MeerKAT, but will face the SKA and all the big modern telescopes, the UGMRT, LOFAR, LSST, all of them, is that you have huge data volumes and huge data rates from all of these telescopes. And it's a major challenge, in my view, to process all of this data and to still be able to do science at the end of it. So we established the Inter-University Institute for Data Intensive Astronomy, IDEA, in South Africa, which could be a center of excellence for doing this. I felt very strongly that data has to be science ready for researchers who are not telescope experts or data processing experts. And I think that that's been a bottleneck for a lot of telescopes, that there isn't always a pipeline which enables you to get science-ready data so that people who are not experts on the telescope can still publish reliable and valid science with it. And I think the SKA pipeline will be critical for that telescope to be productive. So let me talk briefly about what I see as some of the risks of the future SKA telescope building on this idea of pipelines. First of all, when we built the MeerKAT, we were lucky that everybody was in one place. Well, actually in three places, Johannesburg, the Karoo, and Cape Town, but more or less in one place. And the SKA is being built in many countries, many different subsystems, and ensuring that the interfaces are correctly managed and that they integrate well is a major issue. Having pipelines to produce science-ready data, I think, is going to be a huge challenge. I know that a number of Indian scientists are working on SKO software. I think funding for the use and analysis of data from the exciting new telescopes is going to be an issue. We've recently seen a 30% cut in the UK in funding for astronomy and physics. And then schedule slip is going to be an issue, and I think this is going to be a major problem. We know that funding is always an issue, and if funding is adequate, then you can move quicker. If it's not adequate, you can't move more quickly. But there's always that major risk that the schedule will slip. So I want to talk now a bit about the science which is being done by the MeerKAT. This slide I got from Fernando Camillo, who is the chief scientist of MeerKAT, and thanks to him for this. It's a slide he did last year. The telescope, as you know, was inaugurated in 2018. More than 540 articles had been published by the middle of last year. There's over a lot more hours being requested for time than are available. And there's a huge worldwide community of users and collaborations. And I must here say that I have worked with people like Dharamveer Lal and Tiziana Venturi and others who I see are on this call. And it's been a real pleasure to work with them. But there are a number of astronomers from India and from Italy and various other countries who are using the telescope a lot for very exciting science. So in 2009, we called for proposals for large survey projects, which would be over 1,000 hours spread over 5 years. 10 projects were selected. In 2016, they were reviewed, and 8 projects went forward, and they've used 2/3 of the science time. They've all ended in 2025. They included pulsar timing, deep studies of neutral hydrogen in isolated galaxies in the Fornax cluster, ultra-deep surveys for hydrogen, searches for new pulsars, searches for explosive and accreting transients. There have been some very exciting continuum surveys in various fields and very exciting absorption line survey. Let me say briefly, the MIGHTY survey, which I think is very exciting, certainly for me, is a continuum survey, and it does spectral line work as well. But that's going to be taken further by the Super MIGHTY project, which is a collaboration between the MeerKAT and the UGMRT, which will use the very deep MIGHTY fields and the UGMRT to make studies of objects which are found in those fields. Very exciting collaboration, that one. 30% of the time has been used for open time projects and 5% for director's discretionary time. So up to 5% of the time has produced 12% of the papers. So that's been very productive. Some of the pictures, this is the picture that was published when the MeerKAT was launched in 2018. It's a remarkable view of the center of our Milky Way galaxy, showing the area around the black hole, Sagittarius A, and filaments and bubbles, which people hadn't really known about. It's really produced a lot of interesting and exciting new science about what goes on around black holes. Then, even though these papers are a little bit old, 2020, they show some very exciting new discoveries in the study of radio galaxies, the field that I was particularly interested in. On the bottom left, you'll see a paper by a young researcher, Ramatsoku, and she discovered that there were very highly collimated threads of synchrotron radiation between the lobes of radio galaxies spread over thousands and thousands of light years. And on the right is a paper which shows how the jets of energy which flow from around the black hole in the center of a galaxy and act like a snowplow into the intergalactic gas, then flow back and are diverted around the galaxy itself. So you get this remarkable X shape. Here's an example of some of the very deep surveys of neutral hydrogen gas, the Mongoose survey. That goes down to the remarkably sensitive level of 5 times 10 to the 17 atoms per centimeter squared. That very, very low column density enables you to see all kinds of things that weren't seen before. So, for instance, on the top right, a paper by Kurapati and others shows all kinds of low mass dwarf galaxies around one of the galaxies being studied in Mongoose, and shows that there are a lot of gas-rich dwarf galaxies which feed bigger galaxies. There's been a lot of work on high-precision pulsar timing. Some of it you can see there, relativistic and binary pulsars, the timing array, the 1000 pulsar array, globular clusters, surveys of the Magellanic Clouds, and so on. And absolute timing uncertainty down to less than 7 nanoseconds has been very important. In particular, they want to build up a long time base to be able to use this for detecting very low frequency gravitational radiation. This is a very recent discovery which was made by a young student at the University of Pretoria. He discovered the most distant maser, a hydroxyl maser, in a very, very distant galaxy, which was focused by gravitational focusing of a foreground galaxy, and so enables you to see what you wouldn't otherwise be able to see. because it's magnified by this gravitational focusing of the foreground galaxy. A very new development, which I think is very exciting, is called TRON, been developed by Oleg Smirnov and his colleagues. And I've always worried about the fact that there's a huge amount of information in the MeerKAT archives which are not being used. And that's true, of course, of archives of all the other telescopes as well. So how do you use the archival data? Well, what Oleg and his colleagues have done is, after the calibration, they take the data in the image plane and they make images with an 8-second cadence, and then they make a time series for every single pixel. And they found all kinds of interesting transient sources, everything from stellar flares to double peak pulsars. And these wouldn't normally be seen in other transient search projects. So MeerKAT is now being extended because it's such a good telescope. There's a collaboration between the South African Radio Astronomy Observatory, the Max Planck Institute, and the Italian National Astrophysics Institute. Enough. 14 dishes are being added. They're in the SKA design, more or less. They're optimized to be very rigid and very accurate pointing. They're more sensitive than MeerKAT's dishes because they're bigger. There'll be a longer baseline, up to 17 kilometers. There'll be various frequencies covered and a new correlator for all the dishes. And the science commissioning has already started. It's not clear when science time will be available, but they are starting with commissioning. And this will obviously increase the sensitivity of the MeerKAT and its spatial resolution, and it'll be a very exciting instrument. So that's what the MeerKAT extension dishes and receivers look like in the Karoo. Now, the plan is to integrate the MeerKAT dishes into the SKA mid-frequency telescope. And the idea would be to start after you have enough SKA mid dishes to be more or less the same as you've got with MeerKAT. So about 64 dishes. And it's hoped that that would be by 2029. So when you start integrating, many MeerKAT components will have to be retrofitted, which will take at least a year and possibly longer. The question is, how do you do that with minimum disruption of observation? So the South African Observatory has said that the new array must provide guaranteed improvements over the MeerKAT. And of course, there's not a huge improvement. It's about 50% more sensitivity. So not a huge improvement. The capability must exist to coherently continue the pulsar timing array work. No point trying to do all this pulsar timing and then have a big gap in the middle of it. So you've got to demonstrate the system reliability during the period that the timing overlap. And then you've got to minimize the downtime period. So there's already disruption to observations from construction, but that's unavoidable. When will this happen? Well, hopefully by 2029, the integration will start. The current timeline is by 2034. You'll have the whole MeerKAT mid-telescope up and running and ready to do science. Of course, that will depend partly on funding being available. And it's expected that, well, I've expected, let me not speak for anyone else, that the MeerKAT will be about 4 times more sensitive than the current MeerKAT extension. So it will be an improvement. It won't be as ambitious as we'd originally hoped. That's an SK mid dish taken last year. And this is what the future 197 planned dishes will look like when they're built and ready to run by 2034. There are a number of other telescopes on the site in the Karoo, mostly telescopes which are aimed at looking for baryonic acoustic oscillations and the epoch of reionization. So the REACH telescope, which has a lot of international partners, is based there. The HERA telescope, which is again a telescope that has a lot of partners, is based there, has more or less finished its observations. Now they're analyzing those observations. The HIRAX telescope is being built there. It's based partly on technology from Chime, not entirely. Again, a lot of international partners, including India. So we're looking for very exciting results. These all have to complete their observations in time for the integration into SK1 mid. One of the very exciting projects that's taking place now, which I don't understand well enough to explain to you in detail, but I really recommend you look up, is the MeerKAT Large Area Synoptic Survey called MeerKAT. This is using the telescope for intensity mapping of neutral hydrogen. So instead of looking at individual galaxies, it uses a fast scanning technique to look at the broad structure of hydrogen across the history of the universe. And the idea is to give you measurements of how the universe has changed over time, the baryon acoustic oscillations, and the redshift space distortion as the universe has expanded. But along the way, it will also give you a huge radio continuum catalog and various other things, and its first publications have already been made. But I think the methodology that they're using is probably the most promising for these observations, because it gets rid of a lot of the systematic problems that you have in getting rid of the foreground that interferes with the very weak background radiation you're trying to measure. So one of our important mandates was to develop a cohort of young and exciting astronomers. We were funded to start a bursary scheme to take kids from school right up to postdoc. And the whole idea was to build a pipeline. So not just to drop students in somewhere and then leave them, but to actually take students from the earliest stages right up to the stage of being early career researchers. And our key success factors, and I apologize for spelling mistake, was that we designed it as a pipeline. The program staff have been absolutely remarkable. They are very hands-on. They make every student, and there are more than 1,500 students who've been through the program, they make every student feel like somebody cares about them, which is very important, especially for students coming from very disadvantaged backgrounds, disadvantaged schools, very poor homes. They go into university and it's not easy to cope. So the bursary is also big enough that they fund studies and living expenses so that students don't have to take on additional jobs. We also found that we had to provide teachers and laboratories because they didn't have mathematics and science teachers in the local schools in the Karoo. And we also created 5 well-funded senior research chairs at the universities on a competitive basis. They were funded for 15 years, and the idea was to develop critical mass in those universities, and I think it's worked very well. So we did a lot of outreach, and this is a cartoon. We issued a series of comics, which are easily available on the Soraya website, showing how the telescopes work and what people are doing around them. This just shows you the different grants that we've given. So it's for everything from postdoc, PhD, all the way to engineering technology and artisans. So we've developed a lot of artisans as well as astronomers. And this is a breakdown. South Africa still uses racial categories because we're recovering from the period of apartheid where people were categorized racially. So you can see the majority of bursaries have gone to Black African people. but also a lot of women have been brought into the project, and that was very unusual. There's been a very good graduation rate all the way through. You can see well into the 90s, is well above South Africa's other national bursary schemes. And the throughput rate has been very good. That is, students going from an initial degree to a master's degree to a PhD and to a postdoc. You can see there's been a very high throughput rate. And the project also tracks what happens to students when they leave. And you can see a lot of them have gone into research, some have gone into industry, some have gone into universities in other African countries. So it's very valuable to be able to track them. But what you can see is that more than 50% of the students have remained in research either in Africa or in other countries. We also built up an internship program at the Soraya Observatory, and the best performing interns are given full-time jobs. And that's been a very successful program. But what made it successful is that each and every one of our senior engineers and scientists had to say that she or he would be serious about mentoring young people. And they've been exceptionally good. They've really put their hearts into mentoring people. Now, we had to also show that the community was going to benefit from this project. We had a lot of public meetings with the community, a very impoverished community in the Karoo. As I said, very high unemployment. We've got knowledge centers, we've got training of local contractors, because building of roads and so on, we've given as much work as possible to local contractors. We found they didn't really know how to do costing and so on, so we had to train them. We had to arrange bank finance for them. We brought in school teachers, and that made a tremendous difference. One or two really motivated, highly capable young mathematics teachers transformed the whole way the schools saw themselves. And in the center there's a picture of me with the first 5 young students that we were able to give bursaries to go to university to study science and engineering. Before that, nobody qualified from those schools to get into university because the teaching wasn't adequate. So there's also a technical training center in the small town of Carnarvon where artisans are trained, electricians, diesel mechanics, and so on. One of the very exciting things is these young teachers developed robotics in the schools around Carnarvon. And robotics has really taken off big time. And the robotics teams from both the primary schools and the high schools have won competitions all around the world. It's amazing. If you'd been to Carnarvon before we got there, you'd never believed that you would have world-leading robotics. But our work also was to benefit the other countries in Africa. So we started the African VLBI network. We thought we would transform satellite dishes in other countries. It turned out to be impractical and too expensive, but we did transform a dish in Ghana, and we used that to train Ghanaian engineers and astronomers. And this is a completely refurbished 32-meter Ghana radio telescope at a place called Kutunzi, and that has now gone into operation. And there's a very successful collaboration between the South African government and the British government on what's called Development in Africa with Radio Astronomy. It's brought trainees to South Africa and to the UK to train in astronomy. A lot of people have done master's degrees and PhDs, and it's also been extended to big data. So we asked ourselves, if we can't build telescopes in our partner countries, what can we do for them? We said, well, data science is the obvious thing. So we were able to persuade both the South African and the British governments to put a lot of money into big data training, and we've had a lot of workshops around Africa. Again, students studying in UK and South African universities. And it does training across all kinds of things: astronomy, Earth observation, medical imaging, and agriculture, and so on. So a lot of effort has been put into enabling training. Oleg Smirnov and a colleague of his from New Zealand have developed the world's smallest interferometer called TART. This is available on site. If you Google TART, you'll get their website, and you can get real-time imaging of what every TART telescope is seeing around the world. This is the one in Botswana. That's the one in Ghana. And there are telescopes in Bangladesh, Namibia, Madagascar, and so on. And more are being built around the world. France is putting a project manager into the project, and Switzerland, and so on. So women have been a very important focus. Here's a picture of the Women's Data Science Africa School. Women form a big part of our training program. We've used the skills from the project to do a lot of things outside of astronomy. When COVID hit, we were asked by the Minister of Trade and Industry to help the government to develop ventilators. That was done very successfully. There's another project that the Radio Astronomy Observatory is doing now to develop affordable prosthetic legs, because there's a huge need in our public hospitals. There's an e-learning platform. And just the last thing I wanted to tell you about was a new project that is being done by some of the scientists and engineers at Soraya with the Chinese. It'll be a low-frequency telescope to go to the moon on a Chinese space shot in 2029, and it's called the Bounced African Low Lunar Sphere, and you can read about that online. So what excites me now? The new generation of radio telescopes is obviously transforming our studies of radio galaxies, the UGMRT, the MeerKAT, the LOFAR. I wonder at the wonderful pictures we're getting. They're sampling millions of radio galaxies and active galactic nuclei. The image quality is extraordinary. It's led, for instance, to the discovery of so many giant radio galaxies. And I was hoping to have time to talk about some exciting work that Gurab Giri has done, and Tiziana Venturi and others, in showing that you can have fairly young giant radio galaxies. Supermighty will be so exciting. But you need new calibration imaging tools, especially direction-dependent calibration. And you're going to need machine learning tools to find and classify radio galaxies in wide fields. One of the challenges I put to our team very early on was, in the old days, Jocelyn Bell Burnell could discover pulsars because she was looking at paper pen charts and she could see anomalies. What do you do when you have a huge data dump? You can't just sift through it and find the anomalies. So I said, how can we develop an anomaly detection machine? And a lot of work has been done on that. I think the work on Astronomy by Michelle Lochner and her team at the University of Western Cape is outstanding. So I want to thank you for this opportunity to talk to you. I really have enjoyed learning about what Govind did and seeing how close it was, his vision and our vision. He was a visionary, he was a pioneer, he was an innovator, and I hope we learned a lot from him. And thank you very much.
Thank you, Bernie, for a wonderful talk. I'll throw open the floor for questions, comments. Maybe from inside the room first, and then we can take things online. Go ahead.
Why the phase array fielder cancelled?
So there's a question about why the focal plane arrays were cancelled.
We tested them early on, and we didn't think they would be stable enough. The idea originally was that they would work at room temperature, and that they would be very sensitive and very stable. So we made some small focal plane arrays and tested them. And we thought that while the concept was good, they were going to take a long time to mature, and their stability was very difficult to achieve. And in fact, it has worked out that way. The ASCAP telescope, as you know, at focal plane arrays, it took them a very long time to build those to be adequate. I think they are mature now, and I think they will be a wonderful development. But at the time we were building the MeerKAT, we decided to go with what we regarded as cutting edge technology. But what Justin Jonas says was bleeding edge technology, we decided not to go with. We didn't want to take that risk. We wanted to be able to do the best science, best sensitivity, and best dynamic range with what we knew would work.
I guess we have a question from Ronnie Kurz. Ron, could you unmute yourself and go ahead?
Okay. Hello, Bernie. Ron Eakers here. Can you hear me?
I can, Ron, yes.
Okay. I just wanted to reinforce the comments that you made about Govind's influence and perhaps even go a little bit further back when Govind had this vision of a telescope he called GERT, the Giant Equatorial Radio Telescope. And his concept was to integrate, to use the radio astronomy to integrate together all the countries in the equatorial region. And from that, Govind then went to SKA. And of course, it was the SKA concept that I think Bernie got South Africa involved in this mission. So I think it just is an enormous legacy to Govind that you have provided by really implementing part of his vision. I'll ask a question. You talked about this new phase where your incredibly successful MeerKAT will have to somehow be merged into the future SKA mid. And you talked about the technical challenges. What about the cultural challenges as you go from a South African telescope with wonderful international collaborations to being a partner in an international telescope is a bit different?
Let me first say I'm not close enough to know the details. And I also speak entirely as an outsider now. Although in the introduction it was said that I'm still an advisor, I'm not really. So I'll give you my observations, but please bear in mind this is just my view. A lot of the people from the South African project have been absorbed into the international project, some working in Manchester, a lot of them working in South Africa. And there is a lot of cooperation between the South African Radio Astronomy Observatory people and the SKAO people. There will be different ways of doing things. I don't get the feeling that there will be a big cultural challenge. I think what there is concern about is that people understand the MeerKAT telescope very well. They understand the systematics. Obviously, they're still learning, but they understand that fairly well. They are doing research with it. You'll get the SKA, and you'll have to start learning the systematics of that telescope. And that's going to take time. So I'm not sure there'll be a large political problem in the sense of who controls what, because I think that has been agreed a long time ago. Of getting time, again, I'm not sure that will create much of a problem because MeerKAT is already so international. But I do anticipate that there may well be a period from the beginning of integration until you're getting really good science, that is longer than we anticipate, and that may cause unhappiness not only in South Africa but everywhere else. So I hope it doesn't go that way, but it all looks very complicated to me, and I'm very glad I don't have to manage any of it.
More questions? Preeti?
I don't know if I'm audible from here.
Speak up, yeah.
Hello, buddy, Preeti here. So 11 years ago, when we had organized our JETS meeting in Bangalore, and you had, of course, talked about the BLBI, South African BLBI, and it was, I mean, it was a newer also, and everybody else was very excited about this prospect. So what went wrong? I mean, what were the challenges you faced that you couldn't make this happen?
I'm not sure I understood the question completely. Is that about the African VLBI network?
Yes.
So what happened was that the Kutunzi dish was in much worse condition than we'd expected. So we really had to rebuild it from scratch. And the funding that was available from the Ghanaian government was very limited. So it took a long time to be able to get infrastructure in place. We had to train a range of people, including painters and artisans and so on. But just there was a huge amount of work and funding involved in rebuilding the dish almost from scratch. The Department of International Collaboration in South Africa, our Department of Foreign Affairs, also said they didn't have any more funding for further dishes. So there were dishes in Kenya and other places that we were hoping to convert, but it just, the funding wasn't there. It was just unrealistic. And I think now it's probably more beneficial to build new dishes with new technology than it is to try and convert these old dishes. But I'm not really an expert to be able to answer that.
More questions or comments? Let me ask one. So looking back, Bernie, is there anything that you would have done differently? With hindsight, is there anything that you think you could have been done differently and better?
I'm sure we could have done almost everything better. But, you know, nothing really stands out. One of the things that was so important for me was learning to work with engineers. It was such a pleasure because in all the jobs I'd had up to that time, the way people got things done was by holding meetings. And with engineers, we didn't do that. We told them what we wanted and they went away and did it. And then they came back and said, okay, what do you want us to do next? And that was a real pleasure. They didn't hold meetings about meetings. What we could have done better, you know, as I say, there's so many things that with hindsight one would have been able to do, but we had very good support from the Department of Science and Technology and the Treasury right throughout. And I think that was probably the most important factor of all. You can't do a big project like this unless you have a stable funding horizon. If you have to depend on funding from year to year, you can't plan and you can't deliver. So as I say, I'm sure almost everything could have been done better, but offhand, it's very difficult to know. Big projects are, one thing I will say, I think we were very lucky that we came at a particular time. You know, Ron has made the point about a global project. But we landed in a new government which was very flexible, which was very open, and which was very exciting. And I think things are much more rigid now. I think they're more bureaucratic now. I think if we were to try and do this project now, it would be very, very difficult.
Thanks. More questions? Anybody online? If not, let's thank Bernie again for a wonderful talk. And Bernie, we hope to see you in India at some point soon.
I hope we can do that.
Sure, yeah. So thank you very much again, and we'll close the session now.
Thank you very much indeed.
Thanks, Bernie. Great overview.
Thank you very much. Thank you. I hope there was nothing you were unhappy about in what I said.
Oh, I think it's been incredible to watch what has happened in South Africa.
That's good. That's good. How are you, Ron? Are you doing well?
Yeah, I'm managing okay. But like you, don't have to worry about managing anything anymore. But I still think about it.
But you're still doing work. I see you publish still.
Oh, I keep doing research. Yeah, that otherwise my brain would stop working properly, I think.
Yeah, yeah. No, you are lucky. I wish I could do that.